Good day, we are presenting our study entitled Remote Sensing-Based Mapping of Typhoon Egay, Doksuri, Induced Hazards in Talisay, Batangas. A post-event damage assessment approach, this research focuses on analyzing the impacts of Typhoon Egay using satellite imagery and geospatial techniques. By the end of this presentation, we aim to demonstrate how remote sensing can provide timely and actionable insights for disaster response and risk management. Moving forward, I will introduce our research team. The study was conducted by Mr. Amatus, Mr. Chavez, Mr. Iluson, Mr. Bagmoo, and myself. Each member contributed specific expertise, enabling a comprehensive approach to post-typhoon hazard assessment. Typhoon Egay, locally known as Doksuri, brought intense rainfall, strong winds, and widespread flooding across the Calabarzon region, notably in Talisay, Batangas, located near to a lake, experienced both hydrological and terrain-related hazards. Given the urgency in disaster situations, rapid hazard assessment is critical. However, field surveys are often difficult immediately after a typhoon due to safety and accessibility constraints. Therefore, remote sensing services as an effective tool for providing fast, safe, and wide area information that can guide response operations. With this context, we move on the research problem and motivation. This study seeks to answer how severely Typhoon Egay affected Talisay's vegetation, built-up areas, and terrain. Due to limited ground data, traditional post-disaster evaluation is challenging. Local disasters risk reduction and management offices required accessible hazard maps for planning and decision-making. Therefore, this research provides a science-based, map-driven assessment utilizing satellite data to fill these gaps. Next, I will discuss the research objectives. Our study has three main objectives. First, we utilize the satellite imagery data and analysis to detect and evaluate the spatial extent and severity of Typhoon Egay's impact in Talisay, Batangas. Second, we analyze temporal patterns of damage and recovery using multi-date remote sensing data, both pre- and post-typhoon. Finally, we aim to provide actionable insights through evaluating the spatial extent and severity of the impacts. With the objectives clarified, I will now hand over to Carl Justin, who will discuss the related literature on remote sensing in disaster management.
Thank you, Joshua. Next up is the review of related literature. The proponents of the study reviewed literature demonstrating that remote sensing and GIS are widely applied for disaster monitoring and assessment. Existing studies indicate that satellite imagery can detect environmental changes before and after typhoons, map affected areas, and identify hazard-prone zones. Research conducted by Cruz et al. 2019, Abello et al. 2021, and Tumaling et al. 2024 highlights that remote sensing enables efficient evaluation of damages through the analysis of vegetation loss, detection of surface changes, and mapping of flood-affected regions. These findings are directly relevant to the current study as satellite imagery is employed to assess and map areas impacted by Typhoon Egay in Talisay, providing a sound basis. Moving on, this subtopic examines how typhoons generate various forms of environmental damage, including forest loss, vegetation stress, and widespread alteration of land cover. Studies by Magalon and Chiuki 2024 demonstrate the influence of strong winds and rainfall patterns on vegetation damage, while Ignacio 2024 emphasizes the importance of assessing exposure and vulnerability in typhoon-prone areas. These findings are aligned with the current study as Typhoon Egay had similar hazards in Talisay. The observed patterns from previous research provide a framework for understanding why certain areas are more severely affected and the types of environmental damage likely to occur. Next up is the damage assessment and mapping techniques. This subtopic examines various techniques employed to assess damage following disasters. Studies indicate that satellite imagery, UAV data, and automated classification methods are effective in identifying damaged buildings, altered land surfaces, and affected infrastructures. Although the current study utilizes satellite data rather than UAVs or machine deep learning, the underlying principles remain consistent. These techniques highlights the importance of spatial analysis, image comparison, and change detection methods is also applied in mapping effects of Typhoon Egay in Talisay, Batangas. Lastly, the post-event assessment subtopic focuses on using remote sensing and GIS to evaluate damage and guide recovery. Gu et al. 2024 note that damage building detection has advanced from manual methods to AI-driven multi-temporal analysis, while hybrid models improve reliability. Kopika et al. 2024 showed that SAR high-resolution imagery, crowdsourced data, and deep learning enable assessment from regional to local scales. These approaches align with a study which uses pre- and post-typhoon satellite imagery to map and analyze the extent of Typhoon Egay's impact in Talisay, Batangas. Matthew will now introduce the study area and methods.
Our study area Talisay is situated north of Taal volcano and bordered by the Taal Lake. The lakeshore barangays are prone to flooding, while upland slopes are susceptible to landslide and erosion during heavy rainfall. Understanding this geographic context is essential for interpreting the hazard assessment results. Moving forward with workflow, it consists of several key stages, starting with data acquisition to gather satellite imagery and spatial data, followed by pre-processing to organize and align data. We then perform index generation for NDVI and NDBI, feature extraction to import indices, and image enhancement to improve visualization. Afterward, manual interpretation verifies values and compares patterns, followed by decision and classification to identify changes, and accuracy assessments to ensure outputs reflect real conditions. Finally, the final outputs are enhanced clip maps showing pre- and post-typhoon condition ready for analysis. We started with the data acquisition by obtaining high-resolution Sentinel-2 imagery and NDVI data from Copernicus, the European Union's Earth Observation Program. These datasets form the primary spatial inputs to assess vegetation, conditions, and post-typhoon impacts in the study area. Next, during pre-processing, the downloaded bands were carefully organized, checked for spatial resolution, and prepared for raster computation. Proper file naming, alignment, and consistency checks were applied to ensure accurate results. In the feature extraction stage, the compute indices are organized and exported in TIFF format for consistency and lossless analysis. Each layer is saved with clear names NDVI pre, NDVI post, NDBI pre, and NDBI post to ensure easy identification and further use in subsequent processing and interpretation. During image enhancement, the raster layers were clipped to the Talisay boundary using the clip raster by mass layer tool. Each clip layer was renamed and visualized using QGIS symbology, improving clarity and highlighting spatial patterns. Following enhancement, manual interpretation was performed to verify NDVI values for vegetation health, check NDBI values for buildup density, identify and correct errors, and visually compare patterns between pre- and post-typhoon datasets. This step ensured that the map process or the process maps accurately and reflected the real world. During post-processing, each raster layer is refined to improve clarity and quality. This includes adjusting color ramps, removing unwanted edges, checking raster quality, and finalizing symbology. Proper labeling of each layer ensures that the maps are ready for comparison and analysis. In decision and classification, the pre- and post-typhoon, NDVI and NDBI layers are analyzed side by side to detect changes in vegetation health and built-up areas. This step helps identify areas of significant impact and prepares the maps for interpretation and reporting. An accuracy assessment was then conducted to confirm vegetation loss, structural disturbances, and other spatial changes, validating that the outputs correspond to the actual conditions in the study area. Finally, the final outputs consist of the complete set of clip and enhanced NDVI and NDBI maps, clearly showing pre- and post-typhoon conditions.
The DEM map shows the elevation and slope in Talisay, highlighting low-lying areas prone to flooding and steep slopes susceptible to soil movement. This topographic context complements the NDVI and NDBI analysis, helping explain the spatial distribution of typhoon-induced impacts. The NDVI pre-typhoon map shows the vegetation conditions before Typhoon Egay. High values represent the dense, healthy vegetation, while low values indicate the sparse coverage. Establishing this baseline allows us to identify areas most vulnerable to typhoon impacts. Following the typhoon, NDVI values decreased in areas affected by wind, flooding, and soil saturation. Comparing pre- and post-typhoon NDVI highlights zones of severe environmental impact. NDBI map shows the distribution of built-up areas. Pre-typhoon map illustrates the baseline urban and infrastructure conditions. Post-typhoon map reveals the structural damage and surface alterations. Comparing these maps identifies the communities affected by Typhoon Egay.
Our assessment identified major impacts such as vegetation damage, changes in built-up areas and structural exposure, infrastructure disturbance, and combined spatial vulnerability. These findings provide a comprehensive understanding of Typhoon Egay's effect on Talisay, Batangas. In conclusion, remote sensing effectively identified typhoon-induced impacts. NDVI revealed vegetation loss, while NDBI highlighted structural disturbances. DAM offered topographic context showing how elevation and slope can influence flooding and soil erosion. The weighted hazard index demonstrated that structural exposure, vegetation loss, and elevation collectively determine impact severity. Integrating these data sets enabled rapid identification in vulnerable areas, supporting disaster and response and long-term risk reduction. We acknowledge Batangas State University, College of Engineering, especially the Civil Engineering Department, Copernicus Open Access Hub, Pag-asa Data Services, and our faculty advisors for their support. Thank you for your attention. We now welcome any questions and clarifications.